now talking about magnetism. So this is the second half of the electricity and magnetism unit, and our first discussion is on magnetic fields. So to start with, we're going to skip the first few slides because they were all for a physical activity, which we're not going to do exactly right now, but we'll get the understanding of those throughout the unit, so it's not that crucial. But first, let's talk a little bit about the history of magnetism. There's a material known as magnetite, or lodestone. In 1600 BC, it was the Greeks that discovered that this lodestone had the ability to attract other small pieces of iron. Lodestone consists mainly of iron oxide, which is a mineral that was first found near Magnesia in Greece. So that's why we have the term magnetism, because it comes from Magnesia. When pivoted and allowed to rotate freely, a piece of lodestone would come to rest in a north-south position. Because of this property, lodestone was widely used in navigation. Today, however, lodestone is hardly ever used for its magnetic property. Artificial magnets are made from various alloys of iron, nickel, and cobalt instead, which can move a bit more freely than lodestone. When the north pole of one magnet is brought near the north pole of another freely swinging magnet, the magnets repel each other, as shown. Similarly, two south poles repel each other. On the other hand, north poles and south poles always attract each other. So these observations led to the law of magnetic poles. Similar magnetic poles repel, opposite magnetic poles attract. As you know, when a north pole and a south pole are brought close to each other, they begin to attract even before they touch. A magnetic field is a three-dimensional region of space surrounding a magnet that will exert a force on magnetic objects. Magnetic fields are invisible and are more intense at the poles. So what is a magnetic field? You can write down these statements here, which I just kind of summarized on the previous slide. A magnetic field is represented by a series of lines around a magnet. They show the path from the north pole of a small test compass. They show the path that the north pole of a small test compass would take if allowed to move freely in the direction of the magnetic force. These magnetic field lines have specific or several unique properties. You might have noticed already that the magnetic field lines always point from north to south outside the magnet and from south to north inside the magnet. So outside the magnet, we have our magnetic field lines basically flowing towards the south pole, but inside the magnet, we have our magnetic field lines flowing towards the north pole. The field lines never cross one another, and we represent a stronger magnetic field by drawing field lines closer to each other, so they're closer where the magnetic field is stronger, which is usually at the poles, or it is at the poles. So here's some other things to note as well for magnetic field lines. They point from north to south outside, south to north inside. They form this closed loop. They don't cross each other, and they're closer where the magnetic field is stronger. So here's a sketch of a magnetic field around and through a magnet. Notice how we're going from north to south outside and from south to north inside. Describe two methods that could be used to detect the presence of a magnetic field. We could use a compass, we could use iron filings, and if you tap a sheet of paper that iron filings are resting on, they'll tend to orient themselves in the direction of a magnetic field. What does a magnetic field look like when two opposite poles are brought closer together? So that would be the second picture here. You can see that the field lines are kind of resisting each other. They're moving up and away. When we have, that's two opposite poles would be this one here. They're attracting each other. two like poles would be resisting each other. That would be this one here. Sketch the magnetic field patterns expected when the following poles are brought close together. So for a north and a south pole, we would see the lines or the arrows going from north to south. For a north pole, because we flow from north to south, we would see the arrows pointing out away from each other, but they would be opposing each other. For two south poles, we would see these lines kind of going into the south pole, the arrows, but they would still be repelling each other. So why does the north pole of a compass point north if the magnetic field lines outside of a magnet flow from north to south? The interesting thing is our geographic north pole is actually a magnetic south pole. So that's why our magnets point towards geographic north, because the Earth's magnetic field has a south pole at our geographic north. So there's lots of applications of magnetism. One of them is a Maglev train. They have these in Japan. So it's a train that reduces the amount of friction and hence can travel a faster speed by using magnets and a guideway to kind of keep this train elevated. And then the train can kind of move along these maglev tracks. Magnetic resonance imaging is another way of using magnetism. MRI scans can provide far greater detailed images than X-rays can. So that is another use of magnetic fields. Data storage can be done on magnetic drives. Basically, the vectors of the magnetic field can be oriented in such a way that they can be used to kind of note if a bit is a 1 or a 0 on a magnetic drive. You may have seen the aurora borealis if you've traveled up north. That is an interaction between the Earth's magnetic field and charged particles that are entering the Earth's atmosphere from space. So these auroras, they are another kind of, not I guess application or a natural sort of application of magnetic fields on Earth. There are living creatures that can detect the magnetic field and use them. Birds use the magnetic field of the Earth to travel when they're migrating, but spiny lobsters also, they move generally north or south depending on where they want to go, and they use the Earth's magnetic field to guide their way. So here are some applications of magnetic fields. So we talked about the magnetic field of the Earth being oriented so that the south magnetic pole is in our geographic north. That was not always the case. Planets that have magnetic poles, their poles can switch direction. And the Earth has actually switched direction, I think, about 6 times or so. And we're actually due for another magnetic field flip. We don't know when it's going to happen, but it says here on this slide, perhaps that's happening in the next 1,000 years. If that happens, a lot of devices that are based off the idea that the Earth's magnetic field is oriented towards the south, has a north. In our north, we have the South Pole. A lot of those devices would have trouble working. And this last question just gives you an idea. What are some other things that might happen? Well, animals would get confused because they would now kind of screw up their navigation. All of our compasses would now have to be reoriented or relabeled so that the S and the N switch directions, and the east and the west accordingly. Satellites and other things that are rotating around the Earth, or things that are measuring the magnetic field, they would be affected as well. So it would cause quite a bit of concerns for our planet and for the animals that live here as well.